All right, here's the first whiteboard problem. It's going to introduce the magnetic force. And the magnetic force is given by this equation here. Magnetic force equals charge times the velocity cross the magnetic field. If you want to write it to find the magnitude, you can just do QVB, Q times V times B times the sine of theta, because this takes care of the direction. See? And the direction, theta, is the angle between the velocity of the particle and the magnetic field. So imagine you have a region of magnetic field given by these blue arrows. The whole entire region has a magnetic field of a value of 0.18 Tesla in the x direction. We have a proton that is moving relative to this x direction an angle of 60 degrees. That's just this example here. So when we look at that angle, yeah, that's 60, that's the sine of 60 is what we will plug in here. And that's the velocity. And the first part of the question asks, what is the magnitude of the magnetic force? And so we simply just plug that in. That's a real simple case right here. And talk about the cross product. I want to talk about the cross product. Take a look at this right-hand rule here. So everyone can stand up and put their hand like this. I'm going to do it like this. So your thumb is the velocity of the particle. Okay? Your finger, the index finger, is the magnetic field, and your middle finger, which will be perpendicular to the other two, as I've drawn on the board, pointing inwards, see, I'm pointing to myself, that's the magnetic force. Okay, that's how you hold it. And I drew it again here. So whenever you see the notation in textbooks, an X of the circle means into the board, and a circle with a dot, or just a dot, would be out of the board. And that comes from the idea of an arrow. Think of this, imagine this arrow, the cone shape. So if you look at that arrow head on, you'd see a dot as a tip and a circle. Whereas if you look at the butt end, you'd see the tail of the arrow. So that's why you'd see an X. X means into, okay? Sorry, so now that tells you the direction. That's the peculiar thing about magnetic fields. With electric fields, it was in the same direction as the radius vector, right? The electric force, right? And with the magnetic force, though, it's perpendicular to the velocity and magnetic field. So you got to keep track of all three of them. That's why the right-hand rule comes up. It's a little weird. The direction is in a different direction than what the proton was originally going. Okay? And it's also a different direction than the magnetic field is going. Okay? So it's perpendicular to them. So in this case, if the velocity is here and the magnetic field is here, then using my right hand, right? I'm going to just orient myself like this. Magnetic field, velocity like this. My middle finger is still pointing into the board. So the force on this particle is going to go into the board. See? That's the direction of that force. To calculate the magnitude, we simply plug into here. That's the magnitude. And if we were to ask what is the acceleration, the magnitude of acceleration, this is the key idea that we learned in kinematics, that some general force is equal to the mass of the object times the change in velocity. Right? So that's going to be the acceleration. So F equals ma, right? Because in this case, we only have the magnetic force, that is why I'm setting the magnetic force equal to F equals ma. Because that's the force in question. That's the force that we're talking about. If there was another force, then I will add it in, and you'll see that in problem 2. So if you divide this by the mass of the proton, right, 1.67 times 10 to the minus 27th, you're going to get that acceleration. Let's see, meters per second squared. Questions on this? So this is the intro of the magnetic force, how to do the right-hand rule, and how to calculate the acceleration. Questions? All right, let's have the next one. All right, in this problem, we have two forces. Okay, before the first problem, we had just the magnetic field. Now we're going to introduce the electric field, which we're all familiar with. Right? So we have a magnetic field and an electric field, and a particle moving with this velocity. Notice that I'm now using vector notation, ijk. Okay, so these are vectors. We're going to start by asking, what is the force what's the force if there's two phenomena happening, electric field and magnetic field? Well, like with any other forces, like we've learned in kinematics, we do the sum of the forces, right? We do the sum of the forces. What are the forces that are in play? The electric force and the magnetic force, right? So we sum the forces that are there. We know that electric force, we learned, remember from the other equations, is Q times electric field. Because the electric field is the force per charge, so times by charge will equal the force, right? Plus our new thing that we're learning, QV cross B. We notice that they both share a Q, so we can factor that out. So the force net is Q, whatever that charge is, and we're going to use 1.602, that value, and then we're going to do, whereas the essence of the math comes is just that the electric field plus this cross product. Now, order of operations will tell us to do the cross product first, right? Do the cross product first, then add it to the electric field. So let's review cross product real quick over here. What is cross product? We take the vectors, we write I, J, K in our columns, and we write the corresponding numbers underneath the columns that they're associated with, and then we do 3 times 1 minus -1 times 4. That's for the I component. The J component is 2 times 1 minus -1 times 2. And then the K component is 2 times 4 minus 3 times 2. And it follows the pattern plus, minus, plus. See that? And then this is the cross product of V cross B. 7I plus 4J plus 2K. That's what it is in its components. If you wanted to know what direction that's pointing in, that must be pointing perpendicular to what these two vectors are pointing. So if you have two vectors, it would be the perpendicular to those two vectors. That's what this cross product means. So we have that piece. Now we have that V cross B. We can plug that here, and we can do E plus that. So we just add component by component. Add the I's together, add the J's together, add the K's together. You get this, 11I plus 3J plus 0K. Times this by Q, right? Times it by Q, you will get this. We have 3.52I minus 1.6J times 10 to the minus 18. That's taken into account timesing by Q. Newtons, right? That's what's going to have. Because the K component was zeros, that's why I didn't include it here. So that answers our question. What is the force? What is the net force? Given you have a magnetic field and an electric field, it would be this answer here. Okay, see how we got there? And second part is, what is the angle of that force with respect to the x-axis? Well, all we would do is we take the x component of that force, F sub x, divided by F. Why? To get the x component, we do F cos theta, right? F cos theta will give you the x component of that force. So we just rearrange and take the inverse cosine, and we get this. How do I get the magnitude? Pythagorean theorem. 3.52 squared plus 1.6 squared, the square root that's the magnitude of the force. And this is the magnitude of the x component. So this divided by this, the inverse cosine, so I didn't write that. So this whole thing is inverse cosine of that would give you 24.4 degrees. So if I were to ask you, what is the angle with respect to the y-axis, you do the same thing, but you do inverse sine, right? Right? So that's how you would tackle the force and the angle. Questions? Make sense? How to do vectors? So this will apply to what you're doing in packet. All right, so in this problem 3, they're talking about a mass spectrometer shown in this figure. This is a mass spectrometer, basically the physics of how it works. There's an electric field between these plates. We've been used to having that, right, from a previous class. We have and then we have a magnetic field in this region after the charge exits. So basically the idea stems from the centripetal force and the magnetic force. Okay? we have a charged particle. If it moves in a magnetic field, if we do the right-hand rule, with the thumb being the velocity, the index finger being the magnetic field, so that's perfectly lined up with this drawing here. You see how the thumb's going up, the magnetic field's going into the page, the magnetic force, right when it enters, is pointing to the left. And since it's still going straight because of its momentum, right? It's going to go straight and left a little bit. And then the magnetic field is still there, so it's going to go straight, a little bit curved. And you see how, as I go along, my middle finger, the magnetic force, is pointing inwards. So whenever a charged particle enters a magnetic field, a uniform magnetic field pointing in a straight direction, it's going to go in a circular path. Looking at this, we know the centrifugal force is mv squared over r, right? We know magnetic force is qvb, and we set it up such that the angle between the velocity of the particle and the magnetic field are 90. And they are. The velocity is going along this board surface, and the magnetic field is pointing in. So the angle between them is 90. So sine of 90 is 1. So that's why I'm going to just write qvb. We solve for r. We get r equals mv over qb. What's so great about this? Well, it's a mass spectrometer. Knowing the velocity that we're setting those particles at, right? We know the charge. We know the magnetic field. Then if m increases, r increases, right? If m decreases, r decreases. So you see, by the measurement of the radius, that is directly proportional to the mass. You see? So that's why it's a mass spectrometer. Now you know what the mass is by looking at the radius from where it hits, right? Let's do the opposite. Let's say you knew the mass and you wanted to select out the velocities. You could do the same thing, right? So you can know the mass, and then you can change the velocity, the charge on the plates, and make the particle go faster. You know, basically, this changes the direction using the magnetic field and electric field. All right. So the very interesting thing to write down is this: how the units work out. I didn't work it out myself directly, but I probably should. Is that the velocity is equal to the electric field divided by the magnetic field, the magnitudes of them. That's just, the units end up working out. And you can look at the equations. I should probably do this, but I didn't. But if you do, you would probably get this. I trust this. So whatever electric field is divided by magnetic field, you'll get the velocity. Okay? And as we've seen here, this is the r value, right? The r, the radius. And that's how we get there. That's where the rationale comes from, is this. So an interesting application of this is the creation of the first television, the CRT, cathode ray tube television. This is the essence of how that works. So a CRT TV with that long tube, it has an electron gun, and it has two pairs of electromagnets. So they're accelerating electrons, giving them acceleration to shoot them, and then they're using the electromagnets to change the magnetic field so that they change the direction that beam of electrons goes. So they have a pair of electromagnets like this and like this, so that you can control left and right, and up and down by having the electromagnets. And then they program the TV so that it scans across the screen, which is coated with phosphorus, with different colored phosphorus. And so they accelerate the electrons with a certain energy, and when that energy hits the phosphorus atoms, they excite and they fluoresce. And that's how they make a pixel on the old TVs. It used to be the green phosphorus, like fluorescence green. That's why the first TVs were like green. And that's how they make the pixels show up, by controlling the electromagnets, precisely because of this equation, precisely because of QV cross B, that they're able to invent the television. So I think that's pretty interesting. And you'll see another application in the next problem. In this situation, we have two rods, length L. We also have this weird setup of a copper solid rod, cylinder thing, that for some reason has a current going through it. It's like an idealized situation. Just say that there's a battery on the end or something like that that's creating a current going through it. We also have a magnetic field that's pointing down, a uniform magnetic field in this region. So as a check, using the right-hand rule, we can check and see what direction is this rod going to roll. So here we have the direction. So again, my thumb is the velocity of the charges. My index finger is the magnetic field. And then you see that my middle finger is going to be pointing in the direction, in the x direction, let's say. All right? So and the velocity of the charges is the current. The current is going this way. That's the direction the electrons are going. Or you could say the positive. Well, there's not really positive, but that's what direction the current is going. And therefore, the force is going to act this way. So it's going to make this rod move, translate, and it's also going to roll. So there's kinetic energy in translation and rotation. So we got to keep those two things together. Now, let's review real quick the work energy theorem, right? Work equals the dot product, right, of F dot change in distance, right? So to write it out into with the cosine in there, it's magnitude F times the magnitude of the displacement times the cosine of that angle. What is that angle? That angle is the angle between the force direction and the change in distance. So the force direction is in the x direction, right? The change in distance is also in the x direction. So the angle between them is 0, and the cosine of 0 is 1, right? So we know that in this particular case, angle is 0, cosine of 0 is 1. So it's just going to be F times the change in distance, and we're going to say that the change in distance is L. Change in distance is going to be L. All right? So let me just scroll on up to show you guys. Look at this. So let's look at one line at a time here. This is saying right here that the magnetic force is going to be, actually no, let's look at that. Ignore that one. Just look at this one. Kinetic energy translation plus kinetic energy rotation in the I direction plus the change in energy. Well, the change in energy is the work done. The work done. That's initial equals final. Energy is conserved. So that's what you write down. K translational plus K rotational in the I direction plus change in energy equals K translational plus K rotational final. All right, so it wasn't moving in the beginning. And it wasn't rolling. So that's why the kinetic energies in the beginning are 0. Now this is the term I wanted to point out. Well, the force at play here is the magnetic field. The magnetic field is providing that magnetic force. So it's a magnetic force times the change in distance, which is L, times the cosine of theta, which is, we know is 1 in this case, because the angle between that was 0, is equal to 1/2 mv squared plus 1/2 I omega squared. Now, don't confuse this. This I is the moment of inertia, not the current, which we will, so let's write I. To this little subscript, I like to say I of moi, me in French, right? So I of moi, moment of inertia. Just write that. So do that so to not confuse yourself with I as in current. Okay? So that's I of moment of inertia. Okay, and then we look at the force of the magnetic field is going to be here. This I is the current I. Okay? I times D times B times L, cosine of 0, equals 1/2 mv squared times 1/2 And this is the moment of inertia of a rolling rod. The moment of inertia of rolling of a rod is equal to 1/2 mr squared, where r is the radius of that cylindrical rod. Okay, that's what that was in essence. And now what's this? What is omega? Well, let's review real quick. In a circle, we can find the arc length s by doing r times the theta, right? So r times theta gives us the arc length s, right? Now, if I want to, that's the distance it travels along the circle, the circular path. If I take the time derivative, right? R is constant, that doesn't change. So I have r d theta dt equals ds dt. There it is. D theta dt is omega, is the change in angle with respect to time. How fast does the angle change is what omega is. So we get that r omega equals ds dt. What's that? That's the velocity along the circular path. So ds dt is the tangential velocity. See? And now, I guess we don't need to write that subscript, but you know that's tangential velocity. We can say that omega then equals v over r. That's where it comes from. That's omega. So omega squared is v over r, that quantity squared. Okay? So that's talking about the rod, the how fast does that rod rotate? The rod is rotating. If we go back to the picture up here. See this rod? This is what it's talking about. That rod, and it's rotating like this. And it's going to move this direction. See that? It's moving there, it's rotating. And that's what, that's what angle's talking about. Okay, so that clears that up. And let's go back. So we understand this and this, and we understand this. And so here, now it's just algebraic steps. Now you just kind of combine all that together. That's just some algebra steps. So I'll let you guys copy that down. So I'll leave this up to copy it down. And that's what it is all together. And then they just plug in everything, where I here is the current, and we already took into account the moment of inertia. So that other I is not there anymore. So then we have this, just basically the last step is always the plug-in, and then that's the answer. So I would just jot down the answer, I would jot down this. I wouldn't jot down all these numbers, right? That's just plugging things in. Jot down this, and most importantly, this. That's the idea you want to understand. That's the key of this problem, it's that. And to understand this step, and then from here, basically, it's just algebra. Make sense, right? Once you understand these two steps, everything is just algebra.
I didn't get to do this problem on the board, so I'm going to have to record it and show the problem here. So you can pause and read what the givens are as follows. You see the diagram. We have a magnetic field that is perpendicular to the area vector, because this is like kind of like a three-dimensional drawing where the area vector points out towards us. We see the current flows in the clockwise direction. And we have a coil that's not quite a circle, it's an ellipse, but no problem, because we know the area of an ellipse. It would just be pi times the major times the minor axis. And the question it's asking is, what is the magnitude of the torque on the coil? How will it rotate based off of this magnetic field that's being applied to this coil? And we're going to solve this by looking at the torque equation, which we'll show in the next slide. And here the answer is for the torque equation and the torque acting on the ellipse-shaped coil. You can pause the video and take a read. So, we have this as the magnitude, 9.05 times 10 to the minus 4 Newton meters. The important thing is to take away the direction of this torque acting on this loop. We can figure this out by sticking out our right hand and aligning my thumb with the current. So take the leftmost point on the loop. So I would hold my right hand in front of me, my thumb would point upwards, and my index finger would point to the left, because that's the magnetic field. You see that the force is going to be pointing towards you. And that makes sense. So then, therefore, the left side of that loop is going to move towards us. Now, orient your hand so that on the rightmost side of the loop, well, the current's going to be going down, so your hand's going to be a little bit twisted. But then the magnetic field is still pointing to the left, so your hand is going to be, actually, you're going to see the back of your hand. So your thumb's going to point down, your index finger points left still, and then your middle finger is going to be pointing away from you. So the rightmost side of the loop is going to be pointing away from you. And so you have those opposite directions, so that you see that it's going to be rotating along this vertical axis. This vertical axis, if you were to look at this loop on the side and draw a vertical line in the middle, it would rotate where the left side goes towards you and the right side goes away from you. And that is all.